suspect. I think it wasn't very
for
fair.
sure. What was hard? Remembering things that you forgot.
The rotating wave one. I know you went over really well in the review too.
All right, well, we shall see. There is an opportunity for redemption. There will be, so what the plan for the remainder will be, so after class today, I'll post the final assignment, which will be extra credit final homework assignment. And we'll have our usual problem session on Friday to discuss it. We will make up temporary grade based on everything I have next week. And then you can decide what you want to do. Call it a year or take the final, which will be oral exam, a time of mutual convenience for us during finals week. All right? So that's what's going on. Today we'll finish our discussion of multi-electron systems and sort of the basics of the structure of matter, atoms and molecules. And next week we'll talk about how to build more general many-body systems, very important subject in physics, based on the formalism of second quantization, and use that as a launching point to discuss in the final lecture just an introduction to quantum fields, quantum field theory. So that's what's on the agenda, so stay tuned for that because I think you'll enjoy it. All right, so let's see. So last time we emphasized a very important point, which is that if I have some collection of identical particles, then we generally have to think about exchange symmetry. And so, for example, if I have two identical particles and there's a state that I've written down here as a potential state, which involves two possible orbitals that the particles can be in, phi A and phi B. But of course I don't know which is particle 1 and which is particle 2. So I have to appropriately symmetrize or anti-symmetrize. And that spatial wave function can be either symmetric or anti-symmetric, paired with the appropriate spin state so that the overall state is symmetric or anti-symmetric depending upon whether they're bosons or fermions. So if we look, and the spatial wave function plays a particularly important role here. Because if I look at the joint probability density and the position of this two-part system, then I have different kinds of effects. I have effects that have to do with the probability densities associated with each of the orbitals, and then terms that have to do with interference between those orbitals. And identical particle symmetry is only important when this is not negligible. If this is negligible, then I can just forget about the fact that I have identical particles and treat them for all intents and purposes as distinguishable. That means there's the particle localized here, it's that particle. I don't care what its name is, I don't care if it's 1, 2, Amir, or Zeke, it doesn't matter, it's the particle that's there. And it's just a particle in that track, okay? And similarly, so they're distinguishable by their position. And the reason that that's important is because we do measurements locally in space, right? So if I were to look at some observable, I have some apparatus, some detector that has some finite localization, it's going to detect a particle in some region of space, then the effective observable associated with that detector will be 0 outside the detector. Okay? And so I have a detector over here and a detector over here. And then any expectation value I would make with respect to those observables, if I could appropriately symmetrize it. Yeah, actually, I should have a factor of 2 here. Then if I take the expectation value of this properly symmetrized observable with this properly symmetrized wave function, this term will be 0 because there's no overlap, right? And then each one just individually is localized around that particle. So for all intents and purposes, it's as if there was no exchange symmetry to worry about at all. So that's something to keep in mind. Okay? All right. However, when we're talking about matter, ordinary matter, for example, like atoms, molecules, solids, well then, of course, generally speaking, the, say, electrons, which play the substantial role in thinking about the spectra of atoms and molecules, they do overlap. And so we do have to worry about that. It plays a substantial role in thinking about the structure of the atoms and molecules. Okay, and that's what we're going to talk about today. Maybe one day we'll have a course offered in atomic orthostructure again. We haven't taught it since 2011, but maybe we'll teach it again. The simplest multi-electron atom is helium. Okay, so helium has 2 electrons, and we can write down the simplest description of helium, which ignores any of the relativistic corrections, any of the magnetic heat effects, just looks at the Coulomb interaction. So we are in the center of mass rest frame. In this case, the center of mass rest frame is, for all intents and purposes, at the nucleus. You can forget about. I mean, there would be a small correction there, which I'm ignoring at the moment. So I'm in the center of mass rest frame, which means the nucleus is at rest. And then I have the kinetic energy of the 2 electrons. I have the Coulomb attraction of each electron to the nucleus, the alpha particle, and then the repulsion of the electrons from one another. Okay? 1 over 4 pi epsilon equals 1. So we broke this up into 2 pieces. Something I called H0 and something I called H electron-electron. H0 being the sum of the single electron Hamiltonians, okay? And then this is the repulsive energy between the electrons. And we started to look at this last lecture, thinking about, excuse me, solving for the energy levels, the bound states, particularly of the helium atom in perturbation theory. Okay, we can go back and say whether that was a reasonable approximation or not, but let's just try it. So we're treating this as my 0th order Hamiltonian. Maybe before I get to this, So we're going to do perturbation theory here. So I'm going to treat this as my, this is my 0th order Hamiltonian. and this as a perturbation. Okay, so what can we say about the zeroth order Hamiltonian? Let's remind ourselves of what we're talking about here. So this Hamiltonian is the sum of hydrogenic Hamiltonians. Okay? So let's just remind ourselves, I can talk about a hydrogenic atom. Where I have a nucleus with atomic number Z and an electron, right, with some distance there, right? And my Hamiltonian, in this case, in the center of mass, again, is the usual things, the kinetic energy of the electron and the attraction of the electron to the nucleus, all right? So, I ask you, what are the energy eigenfunctions and eigenvalues for the bound states?
Without any other splitting and stuff, right?
That's right. There's no fine structure, no hyperfine structure, none of that good stuff. This is just vanilla, delicious hydrogen. With
air polynomials and the spherical harmonics, is it?
They're
Something like
those are the Laguerre polynomials, right? Yeah.
All right?
Yeah. Laguerre polynomials, that's right. So we have, basically, the point here is that we have the eigenfunctions of this, are the usual things, NLM, right? Is a function of, r theta and phi. They're the radial wave functions. And the y-limbs. Now, let's say that these were the radial wave functions associated with hydrogen. Then the scaling here just has extra z in it. Okay? So if this were hydrogen, z would be 1, but you go through that. And the energy is what? So these are my 5 zeros.
for hydrogen,
Yeah.
normally it's Hartree over n squared.
Yeah, over 2n squared
2n squared.
minus, so it's
Here it's going to be like multiplied by a z.
it's a z squared.
It's a z squared.
So it's 2n squared times the Hartree. Right? So that is, anyway, that's what it is. Okay? So, given that, we can say now what are the zeroth order, what's the energy to zeroth order for this helium atom, ignoring the electron-electron repulsion? Well, there it is. In this case, I have one wave function associated with one orbital, another wave function associated with another orbital, right? And that would be equal to minus z squared over 2, 1 over n squared plus 1 over n prime squared times the Hartree. Okay. So, for example, in this approximation, the total binding energy for the 2 electrons would be what in the ground state? So that would be the state 1s, 2 electrons in that state.
So we go to 1 for both, right? Or
So in this case, these 2, right? So that's 4 times 4 divided by 2, so that's 2. And this is 27.2 electron volts. So that's minus 54 dB. Times 2, no, that, I'm sorry. Let me get this right, something. Times another 2.
Because 1 over n squared is 1, and 1 over n prime squared is 1. So they add.
Oh, yeah, there's 2 of them. Right, exactly. That's, yeah, no, I think I got it wrong. Thank you, 180 dB, that makes much more sense. Okay, so that's what we would have. And then I can ask the question, what are the 0th order wave functions in this case? Well, so to 0th order, the state would, they could have these quantum numbers. However, I have to take into account the Fermi symmetry, right? So I can have, as we just wrote down over there, what I would have is one of the orbitals be for electron 1 be NLN, the other one for electron 2 be NLN prime. But I have to appropriately anti-symmetrize the whole wave function, right? So electron 1 could be in that orbital, and electron 2 could be in this orbital, and then I have to pair it appropriately with, if it's symmetric in space, it has to be anti-symmetric in spin. And if it's anti-symmetric in space, it has to be symmetric in spin. Okay? Now, of course, if both of the orbitals are the same, this expression isn't quite right, Because then there's only, if I have both of them, if n prime, l prime, m prime equals NLM, then the state is, well, they're both in the same spatial orbital. But I can only have what? Singlet or triplet? I can only have a singlet. It must be in the singlet. They can't be in the same spin state. They have to be opposite and anti-symmetric. Okay? All right. So now let's look at the perturbation. So first order perturbation theory tells us that the shift in the energy to first order is given by the expectation value of this. Right? So that's the first order energy level shift for this problem. Let me just remind myself of something. Right. Okay. So now you plug this in, and what you get is the following. That this is equal to two terms, one I'm calling K and one I'm calling J, where this plus sign here is associated with this plus sign here. So this is associated with this singlet, and this is associated with the triplet. Where K is the following. K is the so-called direct term. It's what you would expect to have. I mean, again, going back to just the square of the wave function, there are terms that have to do with the probability that electron 1 is in orbital phi A, probability density, etc. And those two terms add symmetrically because this is symmetric. So I have two of those terms, they add together to give me k, and they are the following. So this is the probability density for orbital 1. This is the probability density for orbital 2. I'm sorry, NLN, N prime, L prime, M prime, times that repulsion energy. Now notice, this integral is symmetric under exchange of x1 and x2. It doesn't matter what I'm calling 1 and 2, okay? So I really had two terms like this, one where this guy was 2 and the other, and this guy was 1, but they added together to give this one term. And then I have this term, j, which is the exchange term. And it's the interference term. LLM x2. All right. Now this is obviously positive because these are positive densities. This is a positive function, so it's positive. This is, turns out, is also positive. Not so obvious, but sure.
Do we need the Hamiltonian term?
Excuse me? Oh, I need the energy, don't I? Yeah. Thank you. Right, so what this says is the following. If I started out in the following way, let's look at, now it turns out that for helium, the only terms, the only levels that are bound are perturbations of the case where one of the electrons is in the 1s state and the other one is in some excited state. Okay? Otherwise, it's under unbound states. So the ground state in the unperturbed case would have been 1s squared. Okay, that's 2 electrons in that. Then I'll have some excited state, which is 1 electron in 1s and the other in 2s. Then I have, you know, some case where I have 1 electron. Well, of course, in the case of hydrogenic-like atoms, this would, well, I'll put it here, 1s, 2p, etc. Okay? Now I add the perturbation. Okay? The perturbation will be a repulsion, so it'll increase the energy, make it less bound. Okay? And in this case, well, I only have the singlet, right? Because I can't have the triplet if both electrons are in the same state. So it goes up by k and then it goes up by j. Okay? That's whatever is downstate. What about this guy? Well, it goes up by k, and then it goes, there's a split in here, right? There's a split in here where this case is the singlet, and this is the triplet. And similarly here. Now, why is the triplet physically more deeply bound than the singlet? Well, the reason is that there's less repulsive energy for the two electrons when they're in triplets. Why? Because of the Pauli exclusion principle. You should think about triplets basically as both electrons in the same spin state. I mean, it's not true you can have the symmetric case, but usually we think about it that way. So if they're both in the same spin state, then the Pauli exclusion principle tells me they can't be at the same position. If they can't be at the same position, then they can't repel each other very much. So in the triplet states, the electrons stay farther away from one another. And because they stay farther away from one another, they repel each other less. And therefore, they're more deeply bound. The symbols. Yeah.
So this J energy though is still a lot bigger than like a fine splitting, hyperfine splitting.
Absolutely. Absolutely. It's a good point.
Because, you know, when we were first doing all the splitting, you know, I was thinking, it looks like there's plenty of room in the spatial orbital for all these electrons, but it's those little perturbations like the fine splitting, hyperfine, they don't perturb the spatial wave functions enough to really get them away from overlap. Maybe I'm not really being clear, but I mean, because those perturbations probably do change the spatial wave function a little bit, or no?
So the question that you're asking is how much does, let's talk about, say, fine structure. Let's talk about spin-orbit coupling. Okay? So we had spin-orbit coupling. We talked about that. We had something like L dot S. Right? Now, the way we dealt with that is we said there's some energy scale associated with this. This energy scale was alpha squared, the fine structure constant squared, times the Hartree. So this was a very small number. And then what we did is we said, really, this energy is so small compared to the splitting between the different orbitals that the effect of this can be seen to excellent approximation by just mixing together the same spatial orbital with different spins, right? So, you know, what we had was a degenerate subspace where we had things like whatever the spatial orbital was, and then we had spin up and spin down, right? And then we cut, and this was, of course, was N Ln times the radial wave function, and then we, you know, had the coupled representation, and we ended up with J, M sub J. But everything was in the same spatial order. However, of course that's an approximation. I mean, there is some off-diagonal coupling that's induced by this interaction Hamiltonian between different orbitals. Except we know that the amount of superposition, the amount of admixture, as it's called, it's not a mixture, it's superposition, but we always say it's that, of the other orbitals that are in this new eigenstate depend on what? They depend on the average value of this perturbation compared to the energy denominators. The energy denominators depend on the energy differences between that. And that's, you know, many EV compared to pico electron volts. So we just generally ignore that. So while what you're saying is correct, the spatial orbital is slightly perturbed by, say, fine structure. It's a completely negligible effect, and we ignore it.
So it doesn't make their overlaps really any kind of significantly go apart from each other at all. So
no.
So this is way down when we're gone.
Right. Well, I think the other thing that you have to keep in mind is it's a different force. It's physically different. This is a magnetic effect. This is an electric effect. Okay? It looks like it has something to do with spin. Well, it does have to. It looks like it's sort of magnetic because it has to do with spin. And that's because of the connection between spin and statistics. So they're just totally, I mean, it's interesting that spin plays a role in mediating electric effects this way, but it does. It's a purely electric effect. And those electric forces are orders of magnitude bigger than the magnetic ones. Oh, I like this is physics. This is good stuff. Yeah.
How about the degenerate perturbation theory? Do we need to consider that at any point, or since one of the electrons has to be in the 1s, then nothing is?
So there, of course, we do have to worry about. We have to actually diagonalize our perturbation in that, but these are the eigenvalues. There's no off-diagonal matrix elements between. Because this is just a spatial, oh, where is it? Whatever. This thing is just a spatial effect. It doesn't, so it's spherically symmetric. So I can just have the diagonal matrix elements. There's no diagonalization to be done, but you're right. We do have to worry about that. All right, so now these, let's just, first of all, just get it, well, come back to this in a moment. I want to just talk a little bit about notation here that you'll see. When we're talking about multi-electron orbitals, then there's different ways, different parts, notations we use to describe them, okay? One is here, this is what's called electron configurations. So this sort of says how I build up those orbitals out of what initial single particle orbitals, okay? They're not really the good quantum numbers anymore. We mix things up together, right? And they're superpositions as we group them over here. At least in this kind of approximation. Secondly, we can say these states have certain good quantum numbers. What are the good quantum numbers here? So once we've done this perturbation and we've mixed these guys together, what is the good quantum numbers? Well, first of all, the total spin is a good quantum number in these states, right? So S, the total spin, either singlet or triplet in this case. What's also a good quantum number is L, the total angular momentum. In this case, it was easy. We really have to think about it, because if I start with S, then, well, I'm adding 0 to something else, so it doesn't really matter. If I had more than one electron, then I'd have to really be careful about that. Okay. Think about that properly. The total, so what one often does then is say, okay, my state here is a state with a given L and a certain degeneracy that is typically written like this. So these would be written, these states would be called the singlet S. This is also a singlet S. This is a singlet S. This is a singlet P and a triplet P. You'll see people, that's standard notation for this.
And why the triplet is 1s? The 1s?
Oh, no, sorry. That's because it's a triplet S. Sorry. Yes, it's a triplet S. Okay. And then when we typically say what the, in addition, what the principal quantum number is here. So this would be 1s, this would be 2 1s, etc. All right. Now, as was just erased over here, you can see the ghost of L dot S coupled. So one in the electron, in the atom, one generally will also have spin orbit coupling. Now, it's a question of how this actually works. This is a very complicated problem in multi-electron atoms. The question is, how big an effect is the spin orbit coupling within an individual, for an individual electron, compared to the coupling of singlets and triplets, or that's coming from the exchange symmetry. Now, I just made this whole rant and rave here about how this is a huge effect compared to spin orbit. But in atoms way up in the periodic table, where each electron is moving very relativistically fast, that could in fact be a much bigger effect depending on how far the electrons are from one another. So you have to ask the question, do I first couple the electron orbit to its spin for each electron and then couple them together? That's called JJ coupling. Or in most sort of the atoms you think about, first, because this is such a big effect, first I couple singlets and triplets together through the exchange symmetry, and then there's a small effect of the coupling of the spin of the orbit. That's called Russell-Saunders. These are arcane names that I learned in graduate school, but no one does it.
We didn't justify yet that perturbation over. So do we need to do that? Or?
We do, but I haven't done it yet. Yeah.
And those two different methods, do they give like a big difference?
They do, and it's really a question of which is sort of what's a big effect, what's a perturbation. So it's like everything else. We're having mathematical models of the physics, and the question is that not a good approximation or not? So we have to really look at those scales in this case. So let me just say just to get the notation right here. So what one would typically write is the following: 2s plus 1 Lj. That's what's called term notation. So for example, I can look at the this is my, for example, configuration in SQP. That got split into a singlet P and a triplet P. Right? And now this gets split by fine structure. So now I ask you, with this crazy notation, what are the possible values of J here? So let's see. This is L equals 1. And this is S equals 0. Yeah. Right? So that means that J can only be 1. So there's one state here. It's the singlet P1.
Does it get split up?
Well, in this case, there is no, it's not split at all because there is no state. Spin is 0 in this case.
There's no change in energy?
No change in energy because there's no spin orbital coupling. Spin is 0. Right? What about this guy? So this is L equals 1 and S equals 1. Okay? Which means J can be 1 or 0. Right? So I have, in this case, the way it goes, it's interesting. I can't even remember this guy. I don't remember why this is true, because it's been 0, but I'm pretty sure that it goes like this. That it's the triplet P2, the triplet P1, and the triplet P0. I have to think about that. Maybe there is something. Oh, no, I'm sorry. The spin is not 0. That's how it goes. Yeah, never mind. Sorry, I got myself confused. Okay, so how big are these scales? So we said here, this was an electronic type splitting. This was really not due to magnetic forces. For, not from the perturbation theory, but the actual value, this is a quarter of an electron volt. That's a pretty big energy on the scale of things. Okay? Whereas these energy scales, this is 10 pico, so it's 10 to the minus 5 eV, and this splitting is 10 to the minus 4 eV. Okay? I could draw it equally to that. That's what it is. I'm going to come back to your question, Amir. I haven't yet forgotten it, but I hope I can come back to it. So what about selection rules? For absorption and emission of light, when I go, say, I try to excite between this level and some of these excited states.
Do we have to worry about whether or not there's an electron in other shells? Or,
So-
or do the two,
Yeah, it's good. So it's a very good question. The way that it works, essentially, and we have to look at the whole overlap of the wave function, but we think about one optically excited electron. Okay? So there's one sort of in the core in this case, and there's one that's excited. Because that's the way we've drawn these. And that's typically what happens when you look at, there are, I mean, real atomic physics, they only sort of to scratch the surface of it. I mean, I think most of the oscillator strength is in when you only have one optically excited. Okay, even when you have to say like through that, something with multiple electrons in the valence shell, you don't have very good oscillator strength between the core and two opticals.
Okay.
It's only one that typically plays an important role. Okay, so with that sort of thought in mind, if I thought about this, well, pretty much all the selection rules that we had before follow. But there's one important question, and that's the triplets and the singlets. So let's look at this. I mean, here this is an allowed dipole transition because we can go from an S to a P, right? So that's an allowed dipole transition. But this gets split by a pretty big amount into the triplet P and the singlet P. Can I go from here to here or here to here? Well, this guy, the ground state is singlet. Can I connect also to singlet or triplet?
you talking about both electrons going up there, or?
Well, what I'm saying is there is a state. Okay. The state itself is of the form, let's come back over here, it looks like this. So it would look like 1s 2p plus or minus 2p 1s with the appropriate singlet or triplet. Okay? I look at the dipole operator that connects this. There'll be dipole operator on electron 1 and dipole operator on electron 2, but I don't know which is which, and it's going to have matrix elements between 1s and 2p. But what about this?
I guess if you start in the 1s, you're in the singlet, so I guess you can only connect to the singlet.
Exactly. There's no way the operators being symmetric under exchange cannot connect singlets to triplets or triplets to singlets. Okay? So we have an important section rule, which is no transitions connect singlets and triplets.
So the helicity of the electron goes to the spatial selection rule. So, in a sense, if we cannot use the sorry, I said electron. I mean photon.
If you repeat the question, I'm sorry.
So the photon cannot use to flip one of the
one of the spins.
yeah, one of the spins.
So it can flip one, but it will also do it to the other in a symmetric way.
Yeah, right.
So the spin can flip, but it will flip the other one.
Yeah.
And it's because of the fact that my, the dipole operator here that I have to count. It would be dipole on electron 1, hence their identity on 2, plus identity on 1, dipole on 2. Or magnetic dipole moment. And that's a symmetric operator. So it does not connect singlets and triplets. I wanted to show you something on the, oh, I guess before I do that, there was, no, sorry, one other thing I want to say about selection rules. So let's think about this now. We have selection rules which tell us that, for say a dipole transition, E1, that delta L has to be plus or minus 1, right? Delta J can be 0 plus or minus 1, but no J equals 0, J equals 0. And similar kinds of rules that we have. Okay. All right, suppose I am in, well, let's draw down here the ground state. Singlet S0. Okay. Well, of course, this is an intercombination. This is a line. It's called an intercombination line. It's forbidden because of what I just said, but it's forbidden in lots of different ways. There's this guy. If I could violate this, if this were not, and we'll come back to this, really perfect good quantum numbers. Well, other than the no triplet to singlet rule, J changes by 1, that's okay. But I can't do this, and I certainly can't do this. This has total angular momentum 0, goes to total angular momentum 0. That is verboten no matter what, okay? These kinds of transitions, though, I should say, we got at these energy levels by doing this kind of perturbation here. Who's to say this was an exact calculation? Who's to say that these are exactly the good quantum numbers? In fact, they are not. There is the true state here I could write as, some probability amplitude of being triplet P1 with a small admixture due to the coupling, due to the fine structure, to a little bit of singlet P1. And therefore, that's allowed. It's not allowed that much. The degree to which it's allowed depends on how much mixing in of singlet P1 there is. So it's going to be a narrow line compared to the allowed transition between the singlet S1 and the singlet P1. That's a very allowed transition. It's going to decay very, very quickly, and it has a very strong oscillator strength. But these are forbidden not only by that, but by these other rules. This transition, turns out, is what's currently being considered for the next generation of atomic clocks. Why? Well, this transition is verboten by a lot. I mean, there's got to be some weird perturbation that mixes in some other orbitals just at some tiny bit to make this not pure J equals 0. But it's a small, small effect. In fact, if, you know, the lifetime of this is a nanosecond, then lifetime of this is 1 billion times longer. The line widths of these transitions in elements in the second column of the periodic table, the so-called group 2 elements, this is a very narrow transition. It's a millihertz line width, which means it's an extremely good oscillator. It's like a pendulum whose frequency is extremely well known. It's the best of grandfather clocks. It's your great-grandfather clock. All right, so now with that, I'm going to discuss this a little bit. That's it, that's probably good. Let's try to put this onto the screen. All right, so just to give you a little sense of scales here, this is out of the undergraduate text by Leboff, if you've never seen that's a really good text. This is a energy level diagram of helium written in the following way. What they're looking at is just the one optically excited electron, okay? So in order to ionize helium, take one of the electrons to the continuum, takes about 24.5 eV. Okay, so this is the ground state. Measured in that way, relative to the energy of the helium ion, where one electron is gone. Now, this is broken up into two columns here, what's called orthohelium and parahelium. In days of yore, it was thought that there were two species of helium because they saw two spectra associated with the transitions between the triplets levels and the transitions between the single levels. And neither the twine met. So they didn't know that there's really, that there were this business of singlets and triplets, right? But there are. So in this guy, you know, I can go from here to here. You know, this guy can decay there. It's of course long. That's a small differential ratio because it's a very small frequency, et cetera, et cetera. Okay, and you see this notation of the. Now notice, of course, you see as I get to the higher principal quantum numbers. So if one of the electrons is way high excited, then it starts to look more hypergenic, right? And then the different L's start to become more degenerate, right? We learned that there's not a strong degeneracy between different L's unless I have a pure 1/r potential. Right? But as it gets higher in the spectrum, I see more degeneracy over there.
And also J becomes much smaller, right?
J becomes small.
J, I mean the
interference
term.
That's right. Just as a comparison, this is calcium. So calcium is a group 2 element. And what we see here are, this is the spectra. These And what you see here is, and the bigger atoms, because there's more relativistic effects, there's more mixing of singlets and triplets. And so these transitions aren't completely forbidden. They're just strongly suppressed. And these kinds of transitions are known as intercombination lines. All right, very good. All right, so how good was this approximation? Now, let's go to this. The board over here. Right. So if I do this, let's just ask about the ground state energy. So what we said here was that to zeroth order was minus 108 eV. What we get if we do this calculation, and it's a boring calculation, I'm not going to do it. We get, this is equal to minus 74.8 eV. Okay? The empirical measure is minus 78.
So that's just calculating the K and J.
That's exactly it, just adding K. There's no J in this case, it's just K. It's a pure, it only has a single. You know, it's okay, but it's not great. I mean, it's a pretty big, I don't know, is it a 5% effect or something like that we're off by? So that's not terrible. Still, it was a perturbation, but not a very good approximation. So what did we do? Now, this of course gets into a whole long story about how you deal with trying to solve approximate methods to solve for the many body energies, right? Because we can't solve this exactly. So we have to think about a different approximation methods. One approximation method which we should talk about, that everyone should know about, is the variational method. To find the ground state. In most computational physicists who are doing anything with having to do with the structure of matter, this is all they're doing most of the time. And what is it? The answer is yes. Based on some kind of educated. All right. So what do I? So what I do is I say, let me guess I know what the wave function is, based on some physical reasoning. Okay. I'm going to say that there's some wave function, I'll call it psi tilde, and it's going to be parameterized by some parameter or set of parameters. Okay. So I make a guess, and if this is to be my ground state energy, and I look then at the expected value of the Hamiltonian. Now I may not have normalized it because putting it with the parameters of my number, so let me just normalize it. Okay? And then this would be my guess for the ground state. Okay? Energy. Now, is this a good guess? Well, what we can show is that this is always greater than the true ground state energy. So let's do that. As I say, it is bounded by the true ground state. The true lowest energy eigenvalue of this is always going to be lower than this. It's not much easier to see. Let's do it. So what I'm going to do is what Adrian always likes to do, put in a complete set here. So these are the true energy levels of the system. Okay? They form a complete basis, and I can insert resolution of the identity over here. And what do you get? You get that this equals the sum over all the true energy levels. This is an eigenstate. Right? Just putting that in. So this becomes an eigenvalue En, and then I just sum over that. Okay? Now this I can write as the E0 plus all of the states not equal to 0, En. Over that.
Should there be a factor like 0 alongside tilde of 0 outside the sum with the
I know. Oh, okay, yeah, the way I wrote it. Yeah, that's right, it's that anyway. This will make sense now. Now it's right over the norm. So I just added some E0. And this is the norm of a vector. So what I get is that this is E0 plus n not equal to 0, En minus E0 times the probability in state n over the norm.
Should it be the absolute square in the denominator or just the inner product?
Oh, it's just the inner product, thanks. Yeah, sorry. Indeed, got myself confused. Okay, so this is greater than or equal to 0. So what that tells me is that whatever I guess, it's always going to be bigger than the true ground state energy. It's bounded from below by the true ground state energy. So the strategy is guess as some function of some parameter that you don't know, and then minimize as a function of this. And that gives you some approximation to the true ground state energy. Now, this doesn't tell me how good an approximation it is. It's not a controlled approximation. It's not like perturbation theory, where there's a Taylor series expansion and it's bounded and we know we go to first order and we can see how it converges. It's more of an art, okay? Now, what we can do is to see how it is, we could try different classes of guesses and see whether this guess versus that guess does better and feel more confident about one guess versus another. But there's really no way, that we said, I know, to basically bound your answer. It's just a guess. What would we guess in this case? Well, so, you know, as I say, it's a whole industry about this in terms of doing, you know, molecular structure, about what the right guesses are and so forth. But we could do something at least reasonably simple in this case. Let's suppose that we say, look, one thing I can guess is that the electrons in helium aren't each seeing the full force of the alpha nucleus. There's a screening of the Coulomb force associated with the attraction to the nucleus that one electron sees due to the existence of the other. So a simple guess, so I choose my variational wave function. Hydrogen-like for some Z effective. This will be my parameter. I don't know what the effective charge of the nucleus is, but it's certainly not the full force of 2, okay? Let me just try that and see what we get. So what would that mean? Well, that would say that my hydrogen wave function, so let's look at the ground state here, the variational wave function for the 2 electrons. Of course, they're in the spin singlet state, but as far as the spatial wave function would be each electron in, so I have the normalization, I have to look that up, it's Z effective cubed over pi, cubed in the minus, bless you, Z effective R1 plus R2 over A. Okay, so each one of these is a hydrogen wave function with y 0, 0. The radioid function is just the exponential. We get a polynomial not there. And then, all right, so this is my variational wave function. Right, this is just the product of 2 hydrogenic wave functions with the Z effective. And the Hamiltonian in this case is what we wrote down over there. I'll just write it again. It's P1 squared over 2 mass of the electron minus 2 electrons squared Z plus P2 squared plus E squared. And now I have to calculate the expected value of the Hamiltonian with respect to this. This is already normalized, so I don't have to derive that normalization. Now, how am I going to do that? So this is equal to, I'll write it in the following way. It's the kinetic energy of particle 1, electron 1, kinetic energy 2, right? Then I have minus 2, I'll explain what I'm writing now in a second, the potential energy, actually I'll write it like this. Okay, where T sub I is the kinetic energy of each of the electrons, and V sub I is minus Z effective E over R, E squared. So it's the potential energy associated with a hydrogenic atom whose atomic number is Z effective. Okay? I just rewrote it that way. Why did I rewrite it that way? Because then I could do these things by inspection. Because everyone remembers the Variational theorem. Maybe. We did it. The Variational theorem was something that allowed us to relate the average kinetic energy and the average potential energy to the total energy, right? So from the Variational theorem, in hydrogen, what we had for a hydrogenic case is that this was equal to minus the energy, and E sub n. And the potential energy was equal to twice E sub n. Okay? So this is then equal to this energy we wrote up over there. This is minus Z squared, so it's Z is 2, so it's 4, right? 2 and 2. So this is 2 E squared over A naught for that, okay? With the effective squared. I'm going to say she writes Z effective squared over 2. Right? That's that energy from the Variational theorem. Let me write it more cleanly because my handwriting is less than stellar. Same for this. This guy over here is minus 2 Z effective squared over 2 E squared over A naught from the Variational theorem. Same for this. And then this I have to just calculate. And luckily Sakurai did it for me. Thank you, Professor Sakurai. And the answer is this term is 5/8 Z effective E squared over A naught. The bottom line of it is that this is equal to Z effective squared minus 4 Z effective plus 5/8 Z effective times E squared over A naught. And you minimize that function, and you find that Z effective is 1.7. It's not quite 2, it's a little bit smaller, it's 1.7. And when you now plug all that in, what you find is that my variational calculation gives me that this is minus 77.5 electronvolts, which is closer. Okay, so, but we could do better. I mean, as I said, this is an art. I mean, here what I did is I said that it's still a central potential. It's still a potential that goes like 1 over R, but with some Z effective. What I really should do is have a potential that's central, but it's not just 1 over R. That is, you know, it's got a stronger, this is my Z equals 2, and this is my Z effective. And it should interpolate between these, so that when the electron goes into the core, it sees the full nucleus and outside the core. And I can parameterize relative to that, do a variational calculation based on such a, and this is the kind of thing that people do, and the kind of thing you'll do for homework next week. Look at that, I almost ended on time. It's a first. All right, we will have a problem session. Problem set's coming, and Good times ahead.